showing that we've got a 10,000 pound force pulling on that frame, and we've got these different members, 3 members. It's anchored at A, and it looks like, now that doesn't show it like we normally show it, but that excuse me, that thing is free to move left and right. Okay, it's not free to move up and down. It's anchored that way, so you can expect some forces potentially at BY, but not necessarily BX. Although he's showing a BX, isn't he? Well, I guess it can't move because it's pulling down, isn't it? And there is it's like a keyed groove there. Now it could actually move back to the left, but since the force is pulling here, there won't be any chance for that to move. So there is a resistance at the wall there, isn't there? I was looking at that as a slider, but it really isn't. Okay.
In the description of the problem, it says the support of B permits horizontal reaction.
Right, because there's a if you really blow that up,
it can slide back.
Yeah, it can slide back and forth, but it can't really slide to the right. So there is a resistance that can push back. You know, the wall, since it's got that key in it, it could slide to the left if this weight weren't here. Okay, so there is a resistance pushing it back to the left. Okay, and that's what they're showing you right here. Do what? Yeah, it would have to be with that 10,000 pounds. Yeah. In fact, I would suggest that there might not be enough wall there to hold it, you know, depending on what that material is, I guess. But that's what we would have to figure out, wouldn't we? If that cross section would be able to hold that. So, but what we're going to do with this is we're going to break this. Well, first we'll do the whole system, just like we did with the others, with the joints. There we go. With the joints and the sections. Then we'll go back and we'll analyze each one of these members and see what's going on with those members. So that's what we're going to be looking at doing here now. So if we draw our free body diagram of that, I can get my mouse to work. We would be looking at something like this for the first free body diagram. We would have line going down this way, something going over this way, and of course we got this member here. Now we know we've got this BX, right? We've got an AY and an AX. Excuse me. This is probably going to be pushing back to the right, isn't it? Because it is pinned, and you've got this 10,000 pounds out here trying to rotate that thing back into the ground, don't you? So the AX is going to probably be pushing to the right, just like BX is going to have to push back to the left to kind of keep that thing stationary. What else do we have? That's all that's going on there right now, isn't it? So if we were doing just what we've been doing up to chapter 4, we would just do sum the forces in the X. So if I ask you to find the reactions at the pin locations and then go in and analyze each one of the members, you would have to do this first, right? Minus BX plus AX. That's all you know, right? But you can say from that AX equals BX, right? You proved that. So then we can go in, leave ourselves a little room, and we'd say sum of the forces in the Y equals 0 equals, well, let's see, we got AY going up minus 10,000 pounds Therefore, when you see those three dots, AY equals 10,000 or 10K, right?
We have to account for the beam or the weight.
Did it ask for that? Did they say that? Yeah, they do have the beam weights on there. So we'll have to, I guess if we're going to do the problem like they got it in the book, we'll have to add those in. So I'm going to have to take this out and change my free body diagram. I didn't put any distances in there either, did I? Got in a hurry. So let's see the, okay, so it says this, let's see, the members of the crane. Members have weights as follows. The post is 1,400 pounds, and that would be right here, right? Right in line with the post. And we've got the boom is 1,500 pounds. Now let's see, it's going to be somewhere about in here, if you will, and that was 1,500. And then this member, what was that? The brace is 900. Excuse me. Okay, and now we got to put some distances in there. We know that the distance from here all the way over is 14 feet. This distance here would have to be 7 feet, wouldn't it? Half of the 14, right? This distance here, can I put it in here? I don't normally put dimensions in the picture, but I'm going to on this one. Let's see, what's that going to be? If we cheat, they're saying 5 feet. Why is it 5 feet? Because we had 10 feet to here, right? So it's 5 feet, half of that. Then we've got we probably need to know from A to B too, don't we? You guys get me all excited and I just don't even put all this stuff on my free body diagram. Now that shows that it's 14 feet to that. And let's see, the distance from A to here is going to be, is that 2 feet? And then the distance, can I do it like this? Just put it here. Distance to there is 12 feet. Or you could say 2 feet in here, couldn't you? Oh yeah, that's, well, from A it's 12. It's 12 from A. Let me put that in parentheses. Okay. Because that's going to be, I'm going to be either relative to A or B depending on how I do my moment. And typically I do it the moment about point A. Of course, who knows, that might change this go around. So give myself a little bit more room here now. Sum of the forces into Y. I think I have everything now, don't I believe. So we had AY going up, minus 900. Oh, let's see, minus 1,400 first. Pounds, minus 900, minus 1,500, minus 10,000. That's a bunch, isn't it? But we still only have one unknown, so we can go ahead and solve for AY. All that goes to the other side of the equation, right? Is it 13,800? See if you had 1,500 and 1,500 would be 3,000, 3,800 plus 10. So 13,800 pounds. And we said it was going up. It came out positive. So it is. So what do you think we're going to be solving for when we do our moment equation? Not quite. Bx. We're used to by, right? But this problem is kind of tilted on us. So we're going to be we only have two unknowns, ax and bx at this point, because by we said didn't have any resistance. Okay. So we do a sum of the moments. You know me, predictable. I'll do it at A. So the 1,400 cancels out, right? Because it's going through the point. Anything else? That's all, right? So we've got 900. It's trying to make this thing go clockwise, which is negative, right? Negative 900 pounds times 5 feet minus 1,500 pounds at 7 feet minus 10,000 pounds at 14 feet plus bx. So used to it. Be careful with that now, because that jump up and get you. You know, if we did something like that on a test, I'd have to mark points off. Bx, and that's 14 feet, isn't it? Yeah. That's it, right? So if we leave bx there, everything else goes the other side of the equation, becomes positive. You take the 900 times 5 plus 1,500 times 7 plus 10,000 times 14. Take all of that and divide it by 14. What do you end up with?
11,071.
11,070? Whoops. Make it a 0. Pounds. We said bx was going to the left. It came out positive, right? So it is going to the left. Well, we said ax and bx were equal, so that would mean ax equals 11,070 pounds going to the right. So this is one of those situations where even though you don't have anything visibly, any forces going left or right to make ax and bx do something, there really is a resistance at ax and bx, isn't there? So we have to remember that. So that's the chapter 4 stuff. Well, then what we have to do is analyze the different members. Now, I think, let's see, the usual procedure talks about there on page 98. It says compute the support reactions, which we just did. Isolate each member as a free body diagram showing all known and unknown pin reactions. Consider each multiple force member individually. Apply the 3 equations of equilibrium, sum the forces in the x, sum the forces in the y, and do a moment equation. Because we do have distances now, again. Okay. Proceed to an adjacent member, carry forward those different forces. I was looking for, there's one thing in here, I think normally what you do if I remember correctly, is you want to try to go with, well, first you would go with a force, a member that has external forces on it. Something, you know, like that 10,000 pounds. You would, because you know that. And I think then the other thing that applies is normally you go with the horizontal first. Is typically